Okay, hello everybody. My name is Liam. I will be the moderator for this presentation. Welcome back to the STEM Fellowship REO Chalk Talks for September. Great to have everybody here this morning, and it is my great pleasure to introduce from the Schulich School of Engineering, Natalie, Ria, Angela, and Juan, who are going to be talking about understanding the world through computational modeling. So thank you guys so much for being here, and I invite you to take it away.
Hi everyone, welcome. So I just wanted to say if you have any questions during the presentation, feel free to type them in the chat. One of us will try and answer you, and beyond that, we'll also do a question period at the end once we've finished our presentation. So just a little bit about me, my name is Natalie. I am in my second year now, which means I've just entered my major, which is electrical engineering, and I'm also going to be taking a digital engineering minor. I am Polish, but I was born and raised in Canada. Last year, when I started my degree, I was able to become involved with the Engineering Student Society at my school. So I was actually a Pi Week director, which is a big fundraiser and charity event at our school every year, and that was lots of fun. And now I'm a social commissioner. I also try to make time for equestrian show jumping. That's something I love to do, and I'm trying to keep it up while still in engineering. And this summer I had the opportunity to do research. It was all at home, obviously with how the world is right now, but I was lucky enough to have some furry friends to help me out and get through the days spent on my computer. For my journey with engineering so far has been fantastic. It's been really hard at times, but it's been very rewarding. I think a lot of people choose engineering because of their interest in STEM and science and math, and although that was part of it, I kind of just decided to take a chance on it. A lot of my friends and family were telling me to give it a try, basically. And I just decided one Sunday morning, I was like, okay, this is what I'm going to do. I applied to the Schulich School of Engineering, and that was the only thing I was set on. And this is where I am, and I haven't regretted it since. And something I'm really excited about is to obviously be a woman in STEM and be part of the change to a more inclusive environment in engineering. And so far it's been great. I think the best thing has been meeting new people and being exposed to the world of research and innovation that was out there. I came in realizing that I didn't know much, but now after my first year I realized that there's even more that I don't know, and there's lots to learn. One thing I will say that I think a lot of people think that engineering is impossible. It definitely isn't. It can be hard and tricky at some times, but if you surround yourself with good people, it's a team effort and it can definitely be done. So now we're going to get into a bit about what is agent-based modeling. I'm going to just play this quick 3-minute video so that you can have an idea of what it is.
Agent-based modeling is a type of modeling in which the actions and interactions of autonomous agents, both with each other and the environment, are explicitly modeled in a computer program. The agents can be nearly anything: animals, people, cities, nations. Usually, the agents follow simple rules and are influenced by the other agents in their immediate surroundings. Let's use an example to show what this means. In this model, there are some fish, the agents, that follow one simple rule: swim straight. When a fish exits on one side, it re-enters on the opposite side. Not very exciting, right? To make things more interesting, let's add a second rule. Occasionally, each fish randomly changes its direction a little bit away from its current direction. This is more interesting, but still not very exciting. The fish aren't interacting with each other. Adding one final third rule makes all the difference. Rather than going more or less in the same direction, each fish moves in more or less the average direction of all the fish in its local neighborhood. This mimics real life. An actual fish in an actual school can't see the entire school, but it can sense the fish close by. Agent-based modeling is much more flexible than other types of modeling, such as equation-based modeling. With enough rules, almost any behavior can be modeled and any phenomenon can be observed. But this flexibility also has its downsides. Agent-based models with too many rules are hard to understand. If there are 20 rules affecting one agent, how are we to know which rule is felt most strongly? For example, what rules are necessary to observe a phenomenon such as the schooling of fish? Could a simpler model yield schooling? Nevertheless, a well-designed agent-based model can be very informative. It can tell us which combinations of behavioral rules for agents and environmental conditions yield interesting behavior such as the schooling of fish. What's cool about this model is that the fish actually form schools based on 3 simple rules. They present a different way to understand how phenomena and patterns can arise from very simple behaviors, which is a hallmark of complex systems. Agent-based modeling is foundational to the science that we do here at the Santa Fe Institute.
So as you saw, agent-based modeling allows us to represent complex systems using simple rules that really focus on the individual agents. There's countless applications of AVM, even within NetLoco, which is the program we use to do agent-based modeling this summer. There's sample models ranging from art and like fireworks displays to psychology to business patterns to neural networks. There's a whole variety. And what's interesting is that the randomness of individual agents can result in consistent patterns on a large scale, which is called emergence. It's when you're not really coding something for something specifically, but you then see a pattern on a system-wide scale. So this form of modeling really allows us to account for heterogeneous populations, while if you're using equations, you're traditionally assuming that the population is consistent or homogeneous and the same throughout. So another quick example is flocking behavior. And think to yourself, why do you think the birds form flocks when they're flying? Or how many rules do you think that govern the birds to make the shapes? Often people believe that they get into this formation because of some sort of social organization. So there's like an agreement, right? There's one bird that leads the other birds and they all follow. And that's how they create these beautiful shapes. But when you look at the code and how this is actually modeled with agent-based modeling, there's only 3 behaviors. The birds avoid bumping into their neighbors. They all fly in a similar direction to their neighbors, and they try to maintain like a certain range relative to the other birds. And it's only 3 simple rules, but you can actually see these simulated in agent-based modeling programs. So as I mentioned before, the program we used this summer is called NetLoco. And this is free to download and you can start coding in it on your own. We're going to post a link to it in the chat right now. But basically, there's kind of 3 components to it. There's the code tab, which is here's a snippet of the code. And the code is created so that people with no prior coding experience can give it a try. There's lots of resources available on YouTube or on the NetLoco site that can help you get started. And beyond the code tab, there's also an information tab, which you would see if you open up the software, and the display and user interface, which you can see, depending on what you're coding for, will have different results. So this is just quickly a forest fire simulation and another one involving acids and bases. So I will switch over now to Juan.
Okay, so now I'll talk about my engineering journey and the model I worked on myself. I'm also just posting the link to download NetLoco on the chat, which is free to download. But first I'll talk a bit about myself. So I'm an electrical engineering student with a minor in computer engineering, and I'm entering my 3rd year. I was born and raised in Monterrey, Mexico, until university when I moved to Calgary for my studies. And a little bit more about myself, my personal life. That on the left is my niece and nephew who live in Seattle, and I like to visit as much as I can. I posted some camping photos because it's something that I really enjoy to do and like to make time for it. And with all the pandemic going on, it's been nice to get some outdoor time. I also enjoy exercising a lot, and skiing is definitely one of the ones I enjoy the most. So that's something I like to take advantage of living in Canada now. But now onto the next slide, Natalie, if you can move on. Okay, so my engineering journey, I chose engineering for various reasons, and quite honestly, for me, it was kind of an easy decision. But one of them is because of my curiosity. I always wonder how things work, just like how my phone works, how just machinery works, how a car works, and everything. And in that same point, there's just so many real life applications, and it just fascinates me to see just how engineering is just everywhere in buildings and machinery and electronics, just in everything. So I just love to see all the real life applications that it has. Uh, and I also joined it, chose engineering because of my interest in those topics and all the science and STEM topics. Um, and then it is also a really important life tool, and I'm saying this because engineering teaches you uh, not just the topics and courses that you learn, but how to problem solve. It's really a way of thinking of how to start and finish a problem. And finally, it just simply amazes me the things that engineering can come from. And I put a picture of a SpaceX rocket because it's just amazing that we can reuse and land a rocket with so much engineering. That there has to be just so much engineering that goes into it. And even in the final seconds of landing, there's like no one really in control of the rocket but the computer itself. So it's just amazing that we can do a successful landing like that. And I also posted the second picture in the middle is a Neuralink. I don't know if anyone has read into that, but it basically a device that's starting to like be able to read brains and can contribute to um, major brain injury uh, development. So that's something that really amazes me too. All the things that can go into that device. But engineering does come with challenges, and first and foremost, it is hard. Uh, but as Natalie mentioned, with the right people around you, you can go through it. And one of the other points I put in here is knowing to not work alone, because at the beginning you try to do everything by yourself, but you find that that doesn't really work in engineering. It really is a team effort. So when you surround yourself with the right people, you can get through problems much better. And something that's also really important for me is to know why something works and not just how it works. So not just doing problems, not knowing the reason why it works. It really um, helps my engineering understanding, but it's also something difficult because it's not always just logical why something works the way that it is. And finally, I want to point out that it's hard to knowing what your end goal is and how to reach it. And what I mean with this is just when you see a problem, it's like, ooh, what can I get from this? What will I reach with this, or how will I solve it? And it's hard to know the steps to get to that goal. And an example of that is me during this agent-based modeling research. I started a model and then I realized it was just too complex and too difficult to get actual results from. So I had to change my modeling approach on that. And now for the next slide. So now actually going to the model I developed, which is a COVID-19 lab room model. And you can see a screenshot here of the setup. I'll switch over and share screen to actually show my model at work. Um, so, okay. So I hope, can you all see my model correctly?
Yep.
Okay, perfect. So first there's the interface tab, which is where you can actually see the model at work and all the setup parameters here in the left and right. And then there's the info tab, which just kind of describes the model, how it works and such. And then there's the coding tab, which is just a bunch of code of how the model is actually constructed. So yeah, I'll show my model. I'll set it up again. So you can see the profs here in green. The students are not quite in the room yet, but there's all these different parameters of how you want to set up the room. So you can vary the room width, height, the number of rows, the number of columns of tables, chairs per table, number of students, lab time. So I made this model like really variable, just because we really want to see how COVID will spread in different variations of the model, and what would be kind of the best lab configuration to minimize the spread of COVID. So then up here to the right, there's an initial outbreak size. I put it at 10 just so we can, when I run the model, we can see how the virus spreads quickly. And then there's percent of groups, just average group size. Then there's some demonstrations, which is uh, when professors just show a part of the experiment in the table. So the tables that are in gray is where demonstrations will be at. And then there's 3 demonstrations. There's a number of sections, which is how many like different experiments there are. So in this case, there's 3, and they're distinguishable by the different colors in the tables. So each color is 1 section, and at some point during the lab, they'll just switch over from section to section. And yeah, then there's the fraction of students per demonstration. So that means that there'll be right now, as it's set to 3, there'll be a third of students per demonstration at a time. And yeah, then there's mask efficiency, pre-symptomatic, and percentage of masked people. So there will be some people that will be masked and some people that are not. So now I'll just run the model so you can actually see how it works. You'll see people coming in to the classroom soon. So if we just wait here a little bit. Yeah, you see a group of friends just coming in. Some are masked, some are not. Also, groups are linked. So this is called a link in that logo, and that's how to identify a group. There comes another student, and that one is infected, and you can distinguish it by the pink color. And as more people get infected, you'll see more people in pink. So now I'll speed it up a bit just so you can see kind of the rest of the model. And then the numbers that the students have is just their proximity to some infected person. And as the closer they are, the higher the number and the higher the chance they get infected. And then now they'll move to a demonstration in a bit. Right about now. Yeah, so they all move to their demonstration, and then they'll switch over to another one. And you can see a chart here that the virus is already spreading. I also have it really so it spreads really fast now. I set it up right now that way just so you can see how it spreads. But yeah, I won't bother to show a lot more because just basically just the same things happen. It just keeps going and runs the full lab period. But the way so this model helps to show us how during different lab configurations the virus spreads. And there's also a contact tracing. So each student will keep track of which students they've been in contact with and for how much time they've been in contact with. And that's part of the experimental procedure I did during my research, just to figure out which were the actual the best lab configurations. So yeah, I'll stop my model. And if I go here to this Excel, I won't bother to show much, but this is just kind of how I tested things. And you can see as the number of students increase, the average number of contacts per person increase. And there's a bunch of tests I did like that way. You can see all the tabs there. So I basically just kept changing one parameter and testing the model to see how things vary with different configurations. So that's pretty much it on my part. I think. Uh, okay, so now I'll pass it over to Ria, which also worked on something on similar lines. Fine.
So yeah, I'm Ria. I worked with Han on the contagion aspect of the COVID-19 model. So a little bit about me. I'm a mechanical engineer. Like I'm just going into my second year of mechanical engineering, and I'm minoring in biomedical engineering. I was born in Botswana, Africa, but I'm actually Indian. So the first picture shows me near, like, in a bookstore. I haven't read a book in a while, but I was a huge bookworm. And it's a pretty good picture, so that's why it's there. Then that's me and my sister on quad bikes. This is in Namibia, so it's a country right next to Botswana. So this is the Namib Desert, and it's really cool because like the desert meets the ocean, and it's the most amazing like sight to see. This is me at the end at a local river. It's called Tamakalane. Try saying that 10 times fast. So yeah, next slide, please. So my engineering journey so far, I honestly got into it the most generic. Like the reason why I got into it is so generic. Like I like math and science. That's something everyone would definitely say usually. But as I got into this degree, I realized that we can test the limits of science and see its application. And we're innovators of the future. So we invent things that haven't been built before. And that's definitely something that draws me to it, and keeps me in this degree. So constant challenges. You constantly have to think out of the box. Why you have to know why things happen and how to apply things, because this is more than just a two-dimensional. Oh, I know atoms mixed together, I know ions form, I know this happens, but you have to know how to apply this sort of situation. Yes, you have conflicts against like personal, academic, and work life. You just need to be really good at time management and all of that stuff. How I overcame these challenges is like I gave myself time and avoided comparing with people, because there are a lot of smart people in engineering. So it can really bring you down and say, oh, his model is definitely better than mine. But you should definitely live in a mindset like I'm doing my best, especially if you are doing your best, and just try and compete with yourself. So I'm also open to working on myself constantly. There's all these constant conflicts and with personal, academic life and everything. I've learned to schedule better. I learned to do better time management, and you just have to be open to changing the way you do things in order for you to work hard. Next slide, please. So basically my model this summer, my agent-based research was the contagion model. So basically my model looks at an arbitrary geographical area, and there are two different agents, like with two different behaviors. Like there's the same type of agent, they're all student agents, but they have two different behaviors. So either they are cautious and social distance, and they try their best not to get infected, or they are social and try and group up. So you see the green people over here, they're actually like grouping up over here. They're trying their best to be next to someone because they're not cautious. And then the purple people are trying to stay away from each other. So I'm just gonna share my screen to show. Can you see that good?
Yep.
Okay, so basically, I have a couple sliders here. You can change these variables to see how and monitor how the spread goes. So you saw the proximity thing for one, of how if someone's closer, they get a higher number. So you know how COVID-19 spreads mainly due to contact. So we're assuming people who are within a 2-meter proximity are definitely contact each other, or they're there for more than 15 minutes, so they start getting the infection. There are also stages of the infection. So we have people who have the disease but don't show symptoms, so they have a less chance of spreading the disease. You can see this when you look at the monitors at the end. So you can see pre-symptomatic means before symptoms show, and then symptomatic are after when symptoms show. So here you can change different variables. You say, oh, I can change the mask variable. I can make all of them masks, and I can say their efficiency is 148%. So efficiency is basically, are they wearing it well enough? Are they using it properly? So basically we can keep it like that. And then testing, you can test people every interval. So you can test, if you turn this on using the switch, you can test 15 students every 5 hours, every 40 hours, and you can see how well this stops the spread. Contact tracing. So if you guys don't know what contact tracing is retracing an infected person's steps. So you say, okay, I am infected with COVID-19 theoretically, and I contact Juan. And then I've also contacted Angela, and then Angela's also contact Natalie. So you go backwards to see who they've contacted, so that you start testing them and seeing if they're infected to try and minimize the spread. So I'm going to turn this off for now. I can show you how it works. So let's start with just having no people social distancing. So everyone's socializing, and there's an initial outbreak size of 10. So what happens is you can assume it's going to be a really bad time, because everyone is trying to just form groups. Everyone is trying to just be together. So the virus spreads really, really fast. Within 13 hours. This is an hourly thing, so that's why they just like jump from one place to another. And then they go home as they become symptomatic, or if they get tested every 15 hours, and then they come back. And when they come back, they are orange, and we assume they cannot get infected again, so that it's easier for us to monitor the spread. So there's slowly more people start showing up, because, you know, different times they got infected, like recovery period is different. There's a lot of extensive research that goes into seeing the range of recovery period, the time they're symptomatic, the time they're asymptomatic, they're pre-symptomatic, and all that. If you have people that are all social distancing, you can assume, and this social distancing radius is like the distance they try and stay away from each other. So like around me, everyone has there's no one around 2 meters around me. So basically that's what it means. So if there's these people, you see like the spread, it does not happen. Yes, there's the initial outbreak size of 10, but everyone's social distancing to the minimum required thing. So that's why it works. And quickly, the outside infections are something that is like, okay, so if I'm at school and then I take transit and then I get infected at the train station and then I come back to school, I have gotten infected. I bring that infection to school. So that's what outside infections is. So you can change like, okay, there's a 13% chance that this person can get infected, that some people can get infected. If you turn on contact tracing, you can see, oh, wait, sorry, I have to use, the only people that contact tracing would work if there's no one like this. So you can see the mean number of contacts that people are making and see how it's just continuously increasing if it's like this, and you can definitely just monitor different sort of situations. And yeah, that's all about the COVID side of the research for the summer. And now we'll move on to, I think it's Angela next, to talk about the homework side. And yeah.
So hi everyone, my name is Angela, as Ria mentioned, and I'm in my 3rd year of electrical engineering at the University of Calgary. So a little bit about myself. My family and I moved from Serbia to Canada in the year 2002, and since then we've gone back to visit really often, and I'm very in touch with my roots, as you can see in the first photo there. I love the outdoors and I love hiking, so this summer, I spent lots of time hiking and exploring Banff and the mountains. I also play classical guitar, and I've played classical guitar for the past 15 years or so. It's probably my greatest hobby aside from engineering. So moving on to the next slide. Oh, it appears.
Looks like we might have lost Natalie.
Yeah. Maybe I'll be able to.
Okay, there we go.
Okay, awesome. So I'll talk a little bit about my engineering journey so far. So when you ask an engineer why they chose their degree, some different answers you'll get are, I was good at math and physics in high school, as you may have already heard in this presentation, or my parents gave me the option to decide between medicine, law, and engineering, and I didn't want to do medicine or law, or some people just join because they're passionate about it. But whatever the reason may be, or your reason may be, your engineering experience can be incredible if you decide to make it that. I decided on engineering because I've always been intrigued by technology and how far research can actually take it. A huge inspiration of mine personally is Nikola Tesla, as you can see in the picture on the far right. He's probably one of the main reasons why I chose electrical engineering in particular. And like him, I do want to have these big ideas and see what I can contribute to an innovative future. So as a degree, engineering definitely comes with challenges. The workload and content may be heavier than what you're used to. And I think this is probably what hit me the hardest in my transition from high school. In high school, I didn't really spend a lot of time studying. So the best advice I can give you in coming into engineering is trying to find a healthy balance between your school life and your personal life. Of course, you may have to spend more time studying than what you're used to, and I do recommend that, but don't overwork and overstress yourself, and take breaks, study with friends, find something that works for you to sort of give you some mental rest, and just don't constantly be stressed. If you try your best, you'll probably do good. So moving on to the next slide, if you want to move on, Juan. I'll talk a little bit about my research. So in taking engineering, you'll have the opportunity to learn skills outside of the classroom, and I highly recommend that. In my case, I had the opportunity to learn a new programming language. This summer, I used an assembly-based modeling software known as NetLogo, as mentioned previously, in order to explore team dynamics in an engineering study group. I developed the model you see here in order to display team dynamics in an engineering study group. I wanted to display team performance in relation to things like team size, the collaborator selection, and the team sociability or extroversion. My findings from this model will describe how to optimize team performance based on the factors I just listed. So for example, as you increase the size of your team, the number of high-performing teams will actually decrease. So this does agree with a lot of research that says that if you work in a group that's too large, the efficiency will actually go down, as students tend to show something called social loafing, in which they don't actually do any work to contribute to the team, they just sort of fake it. So I've modeled it such that students will form teams with students of similar sociability. So high extroversion students will form teams with other students who are also sociable, and vice versa. So this is a huge assumption that I made while modeling. So that probably does affect some of my results, and this could be altered. But what I want to stress, and what's fascinating about my model and NetLogo, is that you can model qualitative factors such as personality traits in students. So you can create a super realistic simulation in order to run experiments and explore any given topic. So I don't know if anyone here has seen The Matrix, but I like to think of it as a mini matrix that you're in charge of. So yeah, that concludes my portion of our presentation. If Natalie is back, she'll discuss her portion of sort of the homework side and exploring student behavior in engineers.
Okay, I was able to get back in. So yes, this is kind of a screenshot of my model. I did research using the motivation equation, which is actually research from Dr. Pierce Steele at the Haskell School of Business at the University of Calgary. Basically, it says that your motivation to do something is your expectancy times the value of the thing you're doing over your impulsiveness, which is just your like a kind of your trait of character, and your delay, just how long it's often far into the future, whether or not you're willing to do it. So my kind of research question was, how can we improve university courses for students without putting the pressure on students to study harder, better, longer, because there's already a lot of pressure to do that. So I was trying to see if you could change the number of assignments or the assignment work time to have students complete their homework faster and more efficiently. So in my model, you have the motivation equation, which kind of sets the base for the student group at the beginning of a course. So there's randomness with that. So even though the expectancy of students is around 50 in the screenshot, there will be randomness within the model. And also I have a parameter that's academically integrated. So some students might be inclined to cheat, or self-development, which just allows students to work on their study skills as they go through a term. So in the end, an interesting emergent pattern was that initially, as students began courses early in the term, they tend to complete their homework at about the same rate, but then as time goes on, the gap grows, which isn't something I coded for, but it's something that has been repeated to us a lot by professors, not to fall behind, because you can quickly, start to lose track of the class. And yeah, that's basically it for my model. So now if anyone has any questions about the models or about anything we've talked about, we'd be happy to answer them.
Cool, thanks. So yeah, we have a pretty small live audience today, but I invite you guys to post any questions that you have in the chat and I can ask them to the presenters. But I'll get started while we wait. So great presentation. Thanks, guys. Really interesting. This is one of the, I think, of the Chalk Talks that I've moderated, this is the first one that's been related to modeling. So that was pretty interesting. So I wanted to first start, and Angela, you touched on this a little bit, but by talking about assumptions when you're building models. So like, I know like in the COVID models, especially, obviously simulating real life is hard. And I can imagine that when you sort of have to define the parameters of the world to a computer, that must be pretty challenging. And I also can imagine that it's easy to get bogged down in sort of the fine details of trying to make things, correct and reflect the real life. So could you guys just talk a little bit about like how, like the process of defining the parameters of your experiment, that other than the, the variables that you're actually interested in looking at, and sort of how you do that and how much time goes into researching to make a a realistic assumption.
Sure, I can answer this question and then I'm sure they can build on it later. So the key to NetLogo and sort of modeling is to try and start with something as simple as possible. So when I was doing my model, I started with simply assigning students their assignment. And then later I started to add factors such as the team extroversion. So basically, how I decided on my assumption is based off of multiple sources. So it is sort of time consuming to read through a series of papers, but what I tried to do is sort of find something that was common among several different research papers and work that into my model. It definitely helps to try to make it sort of primitive. So when I was deciding on students who are low extroversion and high extroversion, I did it on a scale of 0 to 4. If students were assigned the number of 4, they're labeled as high extroversion. And if students are assigned the number of 0, they are low extroversion. And anything sort of in between is neutral, or slightly higher extroversion or slightly lower. So that's just my advice for using that logo. And for modeling something like that is to start simple, start with something primitive, but it can actually turn out to be quite a complex model, even just doing something simple.
And just to build on Angela, is like we have to make a couple assumptions during our modeling thing because we cannot mimic real life perfectly because there's so much things to consider. Because like for example, the COVID model, you can consider that, oh, they've touched surfaces and there's like a probability of getting infected through that. We're just gonna assume certain things so that we can like focus on seeing how this affects spread, like what we're looking at affects spread or what we're looking at affects something else. So these assumptions are just made to make like it easy for us to gather data on how one variable affects something. So yeah.
Okay, thanks. Um, so next, I just want to ask also about sort of the intersections with your research and other fields. So, um, Ria and Juan, there's sort of an epidemiology feel to the modeling that you're doing, and for Natalie and Angela, it's more of a sociology kind of thing. And I think maybe some of the audience might be surprised to see that engineers are sort of dipping into these more social science or liberal kind of fields, and there's sort of a collaboration potential there. And could you guys, I mean, I know that you're undergrads, but could you speak a little bit about sort of the opportunities for collaborating outside of just what people might think of, what people's perception might be of engineering with something like computational modeling?
Yeah, I can touch a little bit on that. So, what is something about engineering is that you always work with other people too. And like as in our model, most of the COVID model for me and Ria, most of our research was on actual like COVID spread. And as I think it was Natalie that mentioned, she looked at some research with Haskell School of Business. So yeah, one thing to definitely consider is that you always have to look at uh, other topics and other areas and look for people who are experts in the areas you want to work on, because engineers, of course, cannot do everything. So you do have to kind of look for get into some other research that is not kind of engineering related and see how that applies to whatever engineering practice you're doing.
And to sort of build on that, for first years and second years, third years, fourth years, you'll usually have the opportunity to do some sort of design class. And in that class, you won't just be focusing on the technical side. Profs do encourage to work on your team dynamic and how to communicate properly with your team and how to present a project. So you do actually gain multiple skills while being in engineering that will help you in your future and in your future workplace. For my model in particular as well, I sort of looked at the psychology side of it. So I researched something like the big 5 personality traits. So engineering is really quite diverse, and you'll actually be able to learn a lot of new skills while being in engineering, which is really interesting.
Cool. Okay.
Oh, sorry.
Um, oh, go on.
Okay, yeah, no, I was just gonna say, like, from some teachers and professors I've had before, they say like they're already doing a lot of research. So for example, as a chemical engineer, they're looking at like stem cell and see how they can like be used in different ways. So he will be doing the application part, and then there will be a stem cell biologist to help. So we will always be working with different fields, with depending on research.
Yeah. So I guess would it be fair to say that if you do have a secondary interest in, a different area, it's definitely possible through engineering to sort of interact with that area too.
Yeah, no, for sure.
Yes,
Cool.
100%.
Cool. Okay. So to move on to some more like career questions, I definitely want to ask, you as presenters are the first again of the Chalk Talks that I've moderated who are in undergrad currently, I think. And correct me if I'm wrong on that. Um, so I think this is a great opportunity because our audience is, late high school, early university. Maybe collectively you can speak to getting involved in research while in your undergrad, why that's important, why you want to do it, and then maybe sort of as a follow-up, you could probably each do this or collectively talk about like why you specifically have gotten involved in the research and what that where your sort of your next steps are career wise.
Okay, so I'll start answering the question. So the reason I got involved in the research is because I just knew it was an opportunity for me to develop the skills of an engineer needs to kind of just through things on their own and kind of figure things out as you go. Because when you start some things in engineering, a lot of times you don't know uh, where to start, but you kind of start figuring things out as you go. So that's an important skill that an engineer needs. And it was also a matter of having some real life applications into this. So directly talking about my COVID lab room model, uh, I could I could use some of my engineering skills to code something that would go into some real life applications. So that's something really interesting and something that a lot of engineers do. So yeah, that's kind of why I got involved, and I'm really grateful that I did because it's been a really good opportunity to develop engineering skills.
I can go next if everyone can hear me okay. I'm not sure how my internet is, but
Yep.
okay, great. So I really wanted to make my summer meaningful somehow this year. And kind of the reason I got involved with this is because I've kind of experienced a few education systems. I was in Poland for a year for school when I was a kid. I also went to a self-directed high school, so I didn't really have classes or anything like that. So, and then I came to university where I went back to classes and stuff. So I kind of been all over the place. So I was interested to kind of research engineering education specifically. I also really liked coding in my first year, even though I don't know, my coding skills aren't that advanced yet. I was excited to work on it more over the summer. Um, Something I will say, like this has been a great opportunity, but research can definitely be challenging if you're coming from your first year, just because your skills are still potentially limited. You don't really understand how the research process works. But that's exactly why it was a great opportunity in the end anyways, because I got to see how it's done. There's some challenges with the remote environment, but there's also advantages to it. And overall, it's a really good learning experience. And it's nice to have been able to work on like a software modeling project over the summer.
I can discuss something next. So I highly recommend research to those who like to challenge themselves and are really open to new experiences and learning opportunities, especially if you're early in your university degree, like say first year or second year, you'll have chances to apply for corporate jobs and summer student jobs, but a lot of the time, since your experience is so limited, you won't really get to do something so exciting. You might just be using Excel or just filing some papers at your first corporate job. So if you have the opportunity to connect with profs or get involved in a research job, you actually do get to do something meaningful and really exciting work and really sort of test your boundaries and just believe in yourself. It is really like, it does sound tedious to start reading through research papers and programming something and debugging your code, but it is actually really exciting. And you sort of think to yourself, I'm really doing this and I'm contributing to some important research. So I do recommend research to anybody who's interested.
Yeah, everyone kind of pretty much covered it all. I have nothing else to add.
Okay, thanks. Yeah, it was pretty comprehensive. So I don't want to keep you too much longer, but I'll ask a couple more quick questions about sort of um, your, experience with your summer research position. So could you tell us a little bit about like what a typical, I realize that things are obviously different right now because you're doing everything remotely, but what a typical week looks like when you're sort of on full-time research, like what what people could expect to be up to on a normal week if they were to take one of these summer research positions?
So I can answer that one first. So basically, the when you're a full-time research student, usually a typical week goes through like involves reading a bunch of research, trying to gather sources. If you're doing, software research, it might even go into debugging your code because like writing the code itself is easier, is like the easy part, but then debugging and finding errors in your code is the harder part. So that takes a while. Also, what else? I guess usually like for us, our supervisors meet us every week and we'd have like daily check-ins to see to like so that our supervisors could could see our progress. So basically this is how it's done remotely. uh Unfortunately, I do not have the experience of how it's done in person because this is like the first research job I've done. And yeah, I think that's how it goes.
Okay, if no one else has anything to add, then let me just, I want to ask one more. This is, you're free to answer this to whatever degree you wish, and I respect it if you don't want to. But in your personal introductions, you all mentioned sort of, you all have like sort of various backgrounds in terms of um, some of you are like, have lived in Canada for a really long time. Some of you have only come here recently. Um, for anybody who's watching who, may be looking at going abroad for university or maybe, is currently abroad relative to Canada and looking at coming here for university. I don't know if there's anything that you could share that might be helpful to a high school student who sort of has that on their mind.
So I guess since I come from Mexico, I can answer this, and because I also just moved to Canada to study. When I decided that I wanted to go abroad, it was majorly for two reasons. One, simply because I just wanted to live in another place and have the experience of living alone. But second is just to take advantage of the opportunities that I could have uh, studying outside of Mexico. So I applied to lots of places in both Canada and the US. And I looked for kind of the university that had the best opportunities in my field. And I'm really glad I did go abroad because it's been a really good experience. And yeah, I've just generally really liked it a lot. And people are very welcoming of international students. So yeah, that's kind of what I have to say on my part.
Okay, thanks. And I'll ask, oh, sorry, was someone going to comment? No? Okay. And I'll ask one last question before I let you go. So you did mention a couple times some advice for existing engineering students, and which I'm sure is helpful. But what about if there's a high school student watching who is really intrigued by um, what you're talking about, and maybe their perception of what engineering is was a little bit, they're learning that was maybe a little bit wrong, and maybe it is right for them, maybe they are interested. Do you have any advice for like high school students, maybe grade 11 or 12, or even like first year university, who haven't made up their mind about majors yet? Do you have any advice to them?
I think I'd say um, to pick a major what makes you feel what very natural. Like I know engineering is definitely difficult and stuff, but you should definitely be passionate about whatever you do. And if you're not sure of if you want to get into engineering, definitely try and talk to people. Try and participate in events like this to see if they would actually be interested in doing something like this. And yeah, I think that's what I would have to say.
I can just add on. I actually have a few friends who have now finished actually their engineering degree, and one of them loves it and she is very passionate about it. The other one, she was saying, she's told me many times that when she was heading into university from high school, she really wasn't sure what she wanted to take. And although she wasn't exactly extremely passionate about engineering to start with, she really appreciated it just because it teaches you so many problem solving skills. It overlaps with so many fields, so you can really find your interests anyways. And just because it's so well recognized as well. So if you do have an interest in STEM, but you're not really sure which way to go, engineering might be a good thing to try, because the skills you gain even from your first year, like they'll be applicable to other STEM fields anyways. So it might be worthwhile just trying taking the leap if you're not sure, but you think you could see yourself in it.
I would also like to add that it's just okay to not know what you want to do immediately, and universities, I think, are making it easier to kind of be undecided or to switch majors nowadays. So yeah, I would say just kind of take the courses that you think you like the most, or the things you want to try, and then from there it's kind of easier to decide. And a good example of this is I knew from the beginning I wanted to do engineering, but I wasn't sure which one. And actually, before starting university, I thought I would pick mechanical engineering. But just seeing on what the classes I took, I liked a lot more electrical engineering, and that's why I chose that career path. So yeah, just don't stress too much about it. It's okay to not know exactly what you want to do, and there's a lot of students that enter university not knowing exactly what they want where they want their career to go.
I have nothing to add. That's some pretty good advice.
Yeah, I think I have to agree. Okay, so with that, we're at about time. So before I let you go, I just want to thank our audience for attending and draw their attention to the fact that the seminar series will continue tomorrow at 6 p.m. Eastern Time. I'll post the link in the chat right now. And the presentation will be from Kate Bourne from the Raj Lab. And she'll be talking about When Gravity Gets You Down, learning about clinical research and postural tachycardia syndrome. So once again, that's tomorrow at 6 p.m. Eastern. That is 3 p.m. Pacific. I just want to take a quick second to say a huge thank you to our presenters today for lending us their time, their expertise, knowledge, and advice. I really enjoyed this presentation. I'm a biologist, and so this is a little bit out of my wheelhouse, but I learned a lot, and it's cool to see, especially as I mentioned, how sort of engineering can really inform various other aspects of research and science. So anyway, thanks again so much for your time, and I wish you luck with going forward with this research and your careers.
Thank you.
Thanks so much for having us. It was a pleasure.
Oh, pleasure's
Thank
mine.
you.
Yeah, thank you.
Bye.